With that, I guess I will get started. Thank you all for joining today, and I'm sure people will filter in over the next few minutes. So here's kind of an oversampled image of TROPOMI, both for the United States and at the urban scale here in the Washington, D.C. area, and I'll show some other urban areas throughout this presentation. I just always like to start with this. It's amazing what we can see from space and all the polluted areas within the United States here. And then, of course, you can do the same thing anywhere around the globe. But really, what today's presentation will be focused on is on US cities. And I'm going to tour through about 10 different cities in the United States. But here's just a snapshot of the Washington, D.C. area, and it's just amazing what we can see from space just in this particular region. Okay, so before going any further, I want to thank the entire Geigert team. It's a relatively small Geigert team, but we're small but mighty. There's been a lot of contributors. I've got most, but not all, of their images here. I'm really grateful for all their help throughout this entire project. And I'll have their images on specific slides that people have contributed to. So you'll see some of these images, most of these images again. All right, so the motivation for this Geigert team and more broadly, this could be grouped into a lot of HAQAST core projects is to better understand the magnitude and spatial patterns of NOx emissions within cities. And really what's driving this is the improved spatial resolution of TROPOMI. This what we still call a relatively new instrument. It's about 3 by 5 kilometers in each direction, but we can oversample it and get it down to the local scale or neighborhood scale, approximately 1 kilometer squared. So the question that this high resolution information is allowing us to ask are the twofold questions. Can we use this satellite data to differentiate NOx emissions within neighborhoods such as near highways, ports, airports, large point sources within a metropolitan area? And can we use TROPOMI data to diagnose EJ issues within urban areas? It's really kind of tied to the previous question as well. But what really the important driver here is, can we do this without the use of an additional model? So just so that we're all kind of on the same page, typically we think of NOx emissions as being really important because it is a driver of surface ozone, but why is not NO2 by itself an important pollutant? I've shown this in some of my presentations in the past, worth reiterating. The NO2 itself impairs cardiovascular functions and causes and exacerbates asthma. We have our 3 collaborators here at GW, Arash, Susan, and Ploy, who've done multiple papers looking at this and found that approximately 1.8 million children develop asthma due to NO2 pollution itself, and it's responsible for approximately 16% of all asthma globally. It's also co-emitted with other harmful pollutants such as diesel PM, other air toxics, heavy metals, and it's inequitably distributed across the urban landscape because it has a relatively short lifetime. So therefore, racialized, marginalized, and minoritized communities experience higher levels of NO2 compared to PM2.5. PM2.5 is an important pollutant, but it generally has a longer lifetime, doesn't have quite as sharp gradients as NO2, generally, not all the time, but generally. And then finally, NO2 is a contributor to impaired natural visibility. So here's just a snapshot from Manhattan looking sort of towards the upper Manhattan, looking south towards I guess the Hudson River, south towards New Jersey, and we can very clearly see this smog layer. This was just 2 years ago now, so there's still pretty bad pollution in New York City caused by NO2 and of course other pollutants as well. So one thing that we've done as part of this Geigert team is we've developed some YouTube tutorials. I've shared this with most of you, but if not, actually Katie will put it in this link in the chat. Check out these tutorials. I forget exactly, 3 to 5 tutorials, but we might add 1 or 2 more in the coming months to help users plot and regrid the data. So that's still ongoing. Hopefully that's something we'll do before the end of HAQAST is over, because I know we get a lot of questions about that. Okay, keep going. In addition, is somebody unmuted? Anyways, I'll let Katie mute if needed. Okay. The one other thing that we've done as kind of a deliverable is we've been working with the University of Wisconsin, and Colleen Heck has been developing some really nice tutorials on how to plot TROPOMI specifically using ArcGIS. So here's some, well, first of all, we have the pre-graded satellite data for downloads, and then she has some tutorials that at this link, I think it might not be publicly available, but eventually it will be. This tutorial link will be publicly available. And then finally, there's this intro for Python for air quality. It's really exciting, that final link on the page. So if you're interested in working with air quality data sets more generally, that link is really great, and really thankful to the University of Wisconsin team for developing all of these documents and software tutorials that I think can be helpful in enabling people to do some of this work themselves and really tailor it to a local scale that, maybe you're not particularly interested with the US NO₂ more broadly, but just a certain city, and this can enable you to do that. One thing that we've developed as part of this Geigert team is this website, TROPOMI NO₂.us. It was live as of a few days ago. I haven't checked today. Sometimes there's bugs in the code. Anyways, but this is from last week, an image from about a week ago. It was a relatively clear day here in the eastern United States, as well as the southwest and southwestern United States. That's not the case last few days here. It's been pretty cloudy. But this is what you can see on a relatively clear day. You can very clearly see the plumes from all the major cities in the eastern United States on the left-hand panel, just on a single daily snapshot, which is quite amazing. If you zoom in, you can start to see individual power plumes and some of the biomass burning or prescribed fires in the southeastern United States. And then you can very clearly see the major cities in the southwest United States as well: Los Angeles, Las Vegas, Salt Lake City, etc., very clearly pop out in this image. On the right hand, we have I'm doing an average compared to I'm doing an anomaly map compared to an average springtime. So I'm comparing March 7th to March through May of 2019. So this gives you a general idea of whether the day was more polluted or less polluted than the typical March day. So it just gives you kind of a rough estimate. And on this particular day, we didn't have too much of the Canadian air mass in the US in contrast to this week. So it was generally a little bit more polluted than average. I think if I were to develop this for today, it would probably see a little bit more blue. That's to come later today around 5 o'clock when we have the measurement. Okay. Also, we have this website, also developed by Nigel Marcus. His pictures there. I really appreciate all of his work on this project. He developed this urbanairquality.online. I encourage you to check out this website for yourself. We have info for 13,000 different cities around the world. So if you're not in DC like myself, check out this website and you can download your data for your city. But so here we have just estimates of the changes in NO₂ concentrations using a land use statistical model. On the top left, on the top right, we then are able to calculate the attributable pediatric asthma incidence per 100,000. We can see that both of those have dropped dramatically in the last 15 years or so. Between 2000 and 2005, we're using MERA2, so it's not quite as accurate of an estimate. So between 2005 and 2019, we have a little bit more confidence because we're using OMI to drive those changes. But then also you can see on the bottom, we can see the actual counts of attributable pediatric asthma for this metropolitan area. And so it's still quite a large number here in DC. We have about 3.5 million people, but somewhere around 3,000 to 4,000 children are getting asthma due to NO₂. So it's not zero. That's the important takeaway. And it's also not, on the order of hundreds, it's on the order of thousands. All right, so I just referenced OMI, and so this is a good time to show the transition between OMI and TROPOMI. OMI was launched in summer of 2004, so we're almost on 20 full years of OMI. Hopefully it makes it 20 full years. But TROPOMI was launched only about 5.5 years ago now. So we can see the early 2000s technology versus the late 2010s technology very clearly in this image. On the center or left-hand side of this panel, we can see TROPOMI on both 1 month, 1 week, and 1 day timeframes. These are all from September of 2019. And on the right, we see the same timeframe, but using OMI. So there is still an overlap between the two instruments, and we can very clearly see that OMI is significantly noisier than TROPOMI. And it's really important to show this. I think the bottom row here is that OMI is really not very useful on a day-to-day basis. It's still useful for doing long-term trends and annual or seasonal averages. I'm not showing that here, but when you smooth it out over a full annual year, you get TROPOMI and OMI start to look very similar to each other. But when you do short time frames, there's very clear differences here. So OMI is great for long-term trends, going trends back to 2005, but TROPOMI is really the driver for a lot of these urban comparisons that is driving this Tiger team. So with that said, I just said that TROPOMI is not the best for trends, but we now have about 5 years of data. So let's see what we can see in the 5 years worth of data. So here I'm using this baseline period of 2018 and 2019 averaged together, and only the summer months, June, July, and August. So a 6-month period is serving as this baseline period. And I'm comparing to the last summer in 2022. And so we'll just give a tour around the country, starting here in the northeastern United States. Most of the major cities in 2022 saw drops somewhere around 10 to 15%. I would include Atlanta in there as well. So this is somewhat consistent with what we'd expect over time. Maybe, they're talking about somewhere around 3 to 4% drop in NO2. Again, generally sort of what we expect. It is a drop. It's not flat. In Chicago, it's a little interesting. It's particularly interesting, and I'll show a little bit, but you can see sort of an increase right along or at least not much of a drop right along the coastline, but interior parts of the metropolitan area, there's a drop. So I think that's interesting. We can also see very large drops in the Ohio River Valley, specifically around Cincinnati, had some of the largest drops, probably due to the power plants in the region coming offline, the big coal power plants coming offline. Conversely, if we look in the center of the country, we've actually seen some, I don't want to say concerning, but definite increases in NO2 in both Kansas and also North Dakota, western Minnesota, on the order of 30% increases. I think there's the potential that soil NOx or some type of agricultural NOx emissions are causing this, but specifically in southwestern Kansas is a natural gas development region. So, and also parts of Oklahoma and Texas as well. So I think a lot of the increases I want to be very clear here, could be potentially related to oil and gas in some of the more southern parts of this red area here. I think you can see my cursor. And then finally, if we go towards the southwestern United States, not much, a small increase in Dallas, really pretty flatlined also in Phoenix area, which I'll discuss more in I think the next slide, but also large decreases in the major cities in California. I've screened out some of the low values here, so I don't want to, if you look at, say, Montana, there's going to be a lot of noise in the instrument, so I've screened out the very low values and really tried to focus on the urban areas in this slide. Now is probably a good time to say, if you have questions, put them in the chat, and I told Katie that she can stop me, or you all can stop me as needed as I transition.
Hey Dan, this is Shobha. I have a quick question.
Sure.
with these increases, I know we saw this similar increases in rural areas when we both did our COVID paper. And Harvard researchers seem to think it is either due to background NO2 from fires, which I don't believe so, because NO2 is so short-lived that I don't think it is getting transported and living longer to be detected in some of these rural areas. But did you think about the lightning knocks? Is there anything related to lightning knocks? It's just puzzling that we don't have an answer for this. Why are we seeing these increases?
Yeah, so I'm what's been really helpful to me at least is this TROPOMI NO2.us because I'll look at that pretty regularly, and we are seeing increases in North Dakota area and as well as Kansas that definitely exceed background NO2 concentrations and cannot be traced back to wildfires. So um, you know, it's how much the wildfires are playing a role is, it's potential that is playing some role in the increase, but I've looked into it a little bit further, and it definitely seems like there's some local enhancement of NO2. Again, hard to pinpoint the exact source, but the key thing that's making me come to that conclusion is that it's day after day in a lot of different meteorological conditions. In particular, in the North Dakota area, it's in the June timeframe, which was really when should be a lot of soil knocks based on my understanding, and also fertilizer application. So my understanding is that there's fertilizer application in like May timeframe, and then the soil knocks is kind of released a few weeks after that. That's sort of, anyways. So yeah, it would look a little different if I showed like the winter months.
And actually picking that up, Dan, if it's soil knocks, could this in part just be a change in this essentially when the warming was?
Yeah,
Or are they actually increasing production and increasing fertilizer use?
I don't know the answer to that.
Okay.
I don't think fertilizer usage has gone down. I have heard that it's probably at minimum staying approximately flat, but it could be going up in certain areas. This is really beyond my purview, but sort of now getting into the hearsay.
Okay.
Yeah.
Related to that, have you looked, I mean, if you look at the trends, were 2020 and 2021 also increasing those areas? Because that could tell you whether this is just something weird in 2022 or not.
Yeah, the short answer is yes, but I'll have that slide in a little bit.
Well,
So,
they were increasing also?
yeah, I have the
Okay.
trends over time. I didn't specifically highlight Kansas and North Dakota, but I do have the image for the Permian Basin and the
Okay,
Bakken area. So you'll see. Okay, let me now go to the next slide. I guess maybe if there's
Sorry.
Oh, sure.
Yeah, sorry, one quick question. Maybe you're sick
Okay.
of talking about this plot, but is there anything related, do you think, in here to which days have the QA filter above whatever cutoff you use, that maybe only certain days are getting counted in these averages during this 3-month period?
Yeah, thanks, Gage, for bringing that up. Yeah, that's definitely a possibility because on particularly sunny days, um, well, first of all, in North Dakota, you're not going to get many winter days in this average because there's so much snow cover. So take that with a grain of salt. Actually, I'm showing the summertime anyways, but yeah, you bring up a good point. There could be some cloud bias. I mean, I don't think it's super significant, but it's potential. Yeah. Okay.
Before you move on really quick, there's
Yeah,
another
sure.
question in the chat. I'm not sure if it
Okay.
was addressed or not, but it reads the reductions in NO2 trends in cities about 10%. Do you think that these are all coming from COVID-19 influence, i.e. less traffic during lockdown and economic activity reduction in general?
Yeah, so this is again, I'm just gonna say that we don't know for sure exactly. I think, I think the short answer is every city is going to be a little bit different. I think if we look specifically at the San Francisco, San Jose area, we know that people are definitely commuting less into San Francisco and staying at home since there's so many tech jobs there. And it is interesting that that also seems to have some of the largest NO2 decreases. I think, but that, you know, I do think a lot of this is, you know, the 10%-ish could be also just be related to people buying new vehicles and some other controls. So it's going to be really hard to disentangle which is COVID related and which is controls. And that's really something that a model would have to, I think Ted is working on that at least a little bit.
I mean, we track the EGU sector in the Midwest, and there are massive changes happening constantly with the shift away from coal. And I would suspect that most of that Ohio Valley stuff is big coal units shutting down. And we have massive lists of the number of shutdowns between 2016 and 2022. It's really pretty amazing how much there is.
Yep, thanks. Yeah, I was going to mention that, re-emphasize that in the next slide. But thank you, thanks, Mark. Okay, let me keep moving on here. So I did want to zoom into the New York City area first, and then I'll show some other cities that have been requested by others. But I'm really thankful and grateful that Michael Geigert has helped out with some of this analysis in the bottom right panel. So here's summer of 2022, so same image as last slide compared to 2018, 2019 average, and New York City, here's this 12% difference. But what's really interesting is that you can see this variability year to year in that bottom, well, in both the spatial plots, but then also the trend line here, where we see this decrease over time, where 2020 was low. We saw an increase in 2021, and then a subsequent decrease that in 2022, and it's sort of similar in 2022 to how it was in 2020. But what Michael Geigert actually was able to do is he took the EGUs from the entire metropolitan, well, not the entire, I think New York and New Jersey. I'm not sure if there's any in Connecticut that could be included here. Anyways, he can maybe comment after I'm done explaining this. But it matched the trends really, really well, actually surprisingly well. So EGUs are definitely a driver of NO2 within cities, at least to some extent. It's hard to disentangle the exact magnitude. You know, certainly mobile vehicles are very important in cities, but we can't discount some of these retirements, as Mark just alluded to, of the EGUs in the surrounding areas near EGUs, power plants. Sorry, if I didn't make that connection for those who are not familiar with that term. But yeah, really interesting to see this pretty strong correlation here.
And I hate to brag on the Midwest, but the shutdowns that happened in New York were tiny compared to what happened in the Midwest.
Yeah, I'm sure.
They just don't have bigger, they don't have big sources. They buy their coal, they buy their power from, Pennsylvania and Ohio and the rest of us.
Yep.
So then what happened in 21? Is it just a recovery from COVID or that bump in 21?
I don't know. Yeah, that's somebody else can probably answer that.
Yeah, I imagine it was the recovery.
Recovery, yeah. Okay.
Well, I was wondering too, to what extent it might be, heating degree days and cooling degree days, and if you have a time period that's really maybe requiring more energy, it'd be interesting because it would also be, you'd imagine people that are driving anyways, also turning their air conditioning up on cooling degree days and therefore expending more fuel in their vehicles as well.
Yeah, I have the cooling degree days for the Bradley Airport, which we use for our ozone anyway. And 2021 was actually less, was 931 cooling degree days. 2020 was the hottest year, which interesting with the economic downturn, even though it was 1,075 cooling degree days, it was still, the economic activity was so low, I guess, you can see the EGUs were just not pumping out as much. 2022 was another hot summer. So that was interesting too. So I'm thinking it may have been part of the control strategy. I think New York shut down a bunch of their little dirty turbines on their barges too, which made a difference. We'll never know for sure, but something was happening.
Thanks. Yeah, that's actually really interesting. I mean, I had sort of the same question as Baron did. So thanks. Really interesting to see that. Okay, moving on. So here, this goes to some of your questions about the sort of the trends over time. I just showed New York City where you had that, 2020 and 2022, sort of similar, but this bump up in 2021. So what I want to show here are some of the major cities on both the East Coast and West Coast, and I'm grouping Chicago in kind of with the East Coast, is that we see these reductions about 5 to 15%. With 2020 generally being the lowest of this 5-year period. Again, generally not always the case. And then I didn't group in Cincinnati here, but very clear. I mean, there's not that 2020 bump, anomaly where it just keeps going down and down in Cincinnati. And again, goes back to what Mark just said, probably a lot of power plants in the region that are shutting down over time. But if we look kind of the central and you can sort of group in some of these other cities in the mountain area. We see this 2020, but I think there's definitely some evidence in both Phoenix and Dallas for this super recovery, and I think the Permian Basin as well for kind of a super recovery. It says it's still 5% lower in 2022 than 2018, but I've definitely seen some days with some pretty large NO2 coming from the Permian Basin. So oil and gas operations definitely cannot be ruled out in this region for at least the Permian Basin. And then Dallas and Phoenix, and I guess Las Vegas to some extent, I think population growth is certainly driving some of the increases here. So interesting to kind of see these dynamics amongst different cities. And of course, every city has its own little stories. I'm not going to have time to discuss all. I think what
the other thing to watch out for in this stuff, the year-to-year mix of the units that are used and their emission rates can have a bigger influence than you think. It's not just about number of megawatts generated. It's sort of that mix. And I know that one of the things we saw in 21, 22 was the mix of sort of plants that were used and how they were dispatched ended up creating some weird differences between 21 and 22. So it almost comes down to, looking at if you want to know, looking at the CEM data and looking at how they dispatch those units on those key days, because it does end up doing some weird things, watching emission rates at individual facilities go up between 2016 and 2022, even though overall emissions are going down, individual units start acting real weird. So just as a side, sorry to hijack.
No, it's fine. It's great to have all this input. Thank you. Yeah, really good point. All right, keep going. Now let's look at, I was just focusing on summertime. Now I'm going to focus on fall 2021 because there was an interesting story, and I'll just kind of get to the point real quick here, is that if we focus on the LA area, if you remember back, I know it seems like ages ago, but this was the height of the supply chain issue where people started to buy a lot of things and the holidays were starting to come up, and we had all these barges just kind of idling off both coasts, but here I'm showing the Long Beach area, and that's highlighted. I think I have yep, here we go. We have highlighted by the red where we saw some of the largest increases right at the Long Beach area, and really amazing that TROPOMI can pick this up, and we can kind of see the plume wafting inland a little bit. Conversely, downtown LA, which is the center one, and the LAX airport, we continue to see pretty large decreases in NO2. So I'm trying to drive this home, is that every city is going to have a different story based on the mix of sources within the city. So it's hard to make kind of these broad conclusions from over a lot of different cities, which I sometimes do. But it's really important to note that your changes in NO2 are going to be very specific to where you live or where in the city you're looking to investigate. So a team from Georgia Tech, Ted Russell's team, and Nash Skipper and Ariana Moore have looked at this even further. And essentially they found the same thing, but what they were able to do, which was really nice, is they were able to use a model to help with this, to disentangle the effects of meteorology on this. And the short answer is that the meteorology wasn't too much of a driver in this particular instance. So that what we're seeing from TROPOMI is really a change in emissions. Some change in meteorology was definitely the changing meteorology was definitely a player here, but we can very clearly see that the emissions were the big driver of the NO2 increases near the Long Beach port, as well as conversely, the decreases near downtown and the LAX airport were also related to kind of this new changing environment after COVID. Now switching to a different team, here is work done by George Mason University, showing the new NEMO inventory. Katie, you can put the paper into the chat if you would like. Yeah, perfect. So that's what's shown on the far right. And I'm comparing this to both the Geigert inventory, which is a global inventory, and the SEDS emissions inventory, which is also a global emissions inventory. Geigert is about 0.1 degrees, or very similar to a 12-kilometer grid that I had been using during grad school, and I think some people still use for the SIP modeling. And then we can see sort of what a global model at about 50 to 60 kilometers, how it resolves New York City, and you really just see 2 good points. And that's, New York City is a huge city. So most cities in the US in a global model will just have one single grid box, compared to NEMO, which is on the far right. Again, you can see so much information. And I just developed this animation. Hopefully it shows, in your screen, showing on my screen at least. And we can very clearly see the differences between emissions inventories, the spatial resolution of emissions inventories. Baron, yes.
Yeah, I just wanted to chime in. I love your point that, if New York has 2 grid cells, right, then most cities have 1, but it's even worse than that, right? Most cities are small, and sometimes they're spread over 4 grid cells because they're on a corner. And so you just smooth out the existence of that city at all. And so it's really important when you're not finally resolving a place to think about that.
Yeah, thanks, Baron. Yeah, and I guess really what I was, so yes, definitely, but I think it's also interesting to see the change also from just 10 kilometers to 1 kilometers. I mean, that was sort of the most surprising part to me, is how much that is how much difference that is. Yeah.
I just had a quick question. Those little dots, I've never seen them before in the NEMO. Those little dots over the ocean, are those some sort of surrogate for shipping lanes?
Yeah, exactly. Yeah, so they, the shipping emissions were actually ingested as point sources. So but yeah, if this were to be used for a model simulation, you have to smear those out a little bit better. But you're right. Yeah, those are shipping emissions, not natural emissions. Okay. And so I just showed New York City. Now I'm going to show a couple. Oh, no, went too far. Now I'm going to show a few other cities. And again, I'm tried to guess who would be on this call. I have Chicago, Atlanta, and the DC area. Again, very clearly see the NOx tied very closely to the roadways. It's harder to see some of the point sources, but they're in there. Okay, so hopefully this animation shows up relatively well on your screen. If not, check out the document online. I think Shobha, can you mute yourself? Thanks. The Chicago area, you can very clearly see that the NO2 observed from TROPOMI very clearly matches the NEI NOx. So this is the NEMO version of the spatial downscaling. So it's using the NEI and then using that information at the county level to then downscale to this 1 kilometer grid. And it's just amazing that we can see pretty good matching here between the two. You know, the hotspot, you know, just to the west of the city matches, and specifically at the airport, you can very clearly see that in the TROPOMI image, as well as some of the refineries and other steel mill just over the border in Indiana area. There's lots of activity here. So TROPOMI can very clearly pick this up, and just amazing what we can see from space. I would just to hammer home that point, here's Washington, D.C. And again, very similar. What I particularly like about Washington, D.C. is you can very clearly see the operations near the Dulles Airport, which is, you know, a secondary or tertiary, in this case, hotspot away from the city. And it's just amazing that TROPOMI can get this type of detail.
Quick question, Dan. How many
from
days
space.
would be stagnant, do you think, per year? I mean, it depends on the city, but I'm just wondering about the sample.
Yep, that's I have the exact number in my paper. It's somewhere on the order of 5 to 10% of days. So of course it has to be sunny. So that's kind of the first thing that sort of eliminates, you know, almost 2/3 worth of the days. And so of those 2/3, you're talking about somewhere about only 25% of those days have stagnant winds. That's, again, ballpark for the northeastern United States, much different for the southwestern United States. And in Chicago, it was actually the worst. It was less than 5% of the days. Windy City gets its reputation for a reason.
Well, Angela could do something about that.
Okay, so here, this is giving a summary of some of the work that I'm about to submit to a journal. This is comparing TROPOMI and the emissions inventories directly, and I've gotten some help from Talma, who has then converted these values into, actually, and Geigert, sorry, I didn't put your image up here. Geigert has helped out a lot on this as well. Help convert the TROPOMI NO₂ into percentiles, and then also do the same thing for the NOx emissions inventory, and then you can compare these two directly because they're at the same in the same units now. What's important here, again, as Michael just brought up, and I didn't actually emphasize, is that we're using days with stagnant winds and that's defined as less than 2 meters per second from the ERA 5 reanalysis. So ideally, I'd reuse some higher resolution model, but for now, I'm just using the ERA 5, which is about 25 kilometers of spatial resolution to estimate the winds only. Okay, so what do we get from this analysis? So I've sort of alluded to this already, but we get really great correlation in all the eastern US cities, again, grouping Chicago into the eastern US here. There's some outliers, which I will discuss in the next slide. I've shown some of this work at HAQAST meetings as well, as some of, or most of you might be familiar with this, but really, again, really important to mention R squared exceeding 0.75 in all of these cases, which suggests that there's just good agreement between the satellite and the emissions inventory, suggesting that both are approximately correct. That's kind of the assumption here. We could get into the details of, maybe the satellite's not 100% correct, and that's, definitely true, but it's just amazing to see such strong correlation between these two data sets. Now I'll discuss some of the outliers in some of these cities, and on the paper I go into all 10 cities, but here I'm just going to show a few of the cities. Here's Chicago. So I did show previously, 3 or 4 slides ago, that there was this great spatial, qualitative agreement between, and actually quantitative in the last slide, agreement between TROPOMI and the inventory directly in Chicago area. However, there are some outliers that were highlighted on the last slide. And so I've actually grouped these to individual zip codes, and I'll just go through this briefly, but the wealthiest zip code in Chicago area is the 643. And that is also the area where there's the largest difference between the inventory and the satellite. And also we see a big difference just north side of Chicago as well. These are generally wealthier neighborhoods, again, generally. And far north is a couple of retired power plants, including in South eastern Wisconsin. So that's what's driving some of these red areas in the far northern. But some of the red closer to the city is probably due to wealthy neighborhoods having less NOx than what the inventory is suggesting. Conversely, in the southwest side of Chicago, where there tends to be a few more warehouses, a few more transfer facilities, rail yard to trucks facilities, we see potentially that there might be some missing sources of NOx, particularly driven by idling vehicles, although it could be other machinery operating at these transfer facilities or warehouse facilities. I think it's still TBD. Had a lot of discussions with LADCO offline about this and also in previous calls, but I think there's at least some evidence here to show that warehouse emissions from idling vehicles near warehouses might be underestimated in typical emissions inventories. I know that there's now new tools to add them in, but previously it seems like there might have been a NOx, this missing NOx. But this is just Chicago, and I see similar themes in other U.S. cities. I'm just going to show New York City, but we also see a similar theme in Atlanta as well, where some of the wealthiest counties in the New York City metropolitan area, Westchester County, Bergen County, Suffolk County, kind of sort of, I know the Hamptons are way out there, but generally it's a little bit more wealthier area. We're seeing some of this red, which again would mean generally an inventory NOx overestimate. Conversely, in central New Jersey, where there are some very large warehouses, again, it's a little bit more suburban. So it's hard to pinpoint, it's hard to directly tie this to warehouse emissions directly, but it is interesting that areas where we know that there are a few more warehouses, there tends to be this blue color. Also, I think what's interesting here is that we see blue in Staten Island and a little bit of red in Manhattan. Again, there's this socioeconomic difference between these two boroughs, as well as probably less public transportation options in Staten Island. So interesting that we can pick this out from TROPOMI. So with that, I've hammered on this point for a little bit in the last few slides, is that warehouses seem to be an emerging topic of something that we should really pay attention to. We have here at GW, Geigert working on this, but I'm going to show some of the work from Georgia Tech, specifically focused on the Fontana region, just to the east of the downtown LA. And this has a very high density of warehouses and distribution centers. If you want to join this warehouse tiger team, email me if you'd like to be involved. You'll have my email address. We're meeting semi-regularly and happy to discuss specific questions that you may have for this. But just very preliminary analysis from this team that they have looked specifically near the Fontana area is that we see kind of this very large NO2 plume coming from LA in all the years, but we do also start to see kind of an increase in NO2 between 2018, 2019, and 2020 in this area that's highlighted by this white box. And then also the warehouses, which are just kind of on the southeast part of this box here. So hard to disentangle this specifically to warehouses. I know I want to make that caveat very clear. It could be related to some other activity, specifically in the area, or some other change in wind patterns. And so the team at Georgia Tech is actively looking at this, and hopefully I'll have some updates in the coming months on this particular topic. Going further, talking about some more work that Georgia Tech has done, specifically looking at the Atlanta airport. I know that's been a concern from a few of you, that both the Atlanta airport, but also airports more generally. One thing that they found in a paper, I believe published last year, was showing how that if you do a better job of vertically estimating the emissions, you get better agreement between the satellite data and the model, which is shown in this. So 3D Atlanta would be a better representation of the vertical emissions versus putting them all at the surface. If I got that wrong, Ted, please correct me. Okay, moving on to some other work. These are generally more from the core projects of teams, but I want to also highlight some of the work that Talma has done. Again, this has been covered a little bit at some previous HAQAST meetings, but worth reiterating here. Check out her paper, which Katie just put in the chat. But I think it's really interesting to see that she was able to show that the ozone production becomes a little bit more NOx sensitive, at least in the New York City area. I think there's some evidence potentially also in the Maryland area, because we're seeing a larger increase in formaldehyde compared to NO2. So we see an increase in formaldehyde, a smaller increase in NO2, and therefore the ratio of formaldehyde to NO2, which is an indicator of an ozone production regime, actually going up. So I encourage you to check out her paper if you want more information. And also Arlene's talk, I'm sure she'll discuss some of this at the next HAQAST meeting. This is new work coming out of both the Tiger team and the core project from Tracy Holloway, is trying to better understand the correlation between the satellite and the surface. And I know that's always kind of a question amongst a variety of different people, both research and stakeholder communities. I thought generally we're seeing better correlation from this analysis in the suburban and rural areas, noted by these colors up here. The R² is higher for these two areas. Urban, there's a little lower correlation, and that's partially driven by just the spatial, TROPOMI. There's going to be a lot of spatial heterogeneities of NO2 in urban areas, and it's going to be hard for TROPOMI to pick up on that. What is also interesting is that TROPOMI is actually most correlated with the early morning hours NO2 in cities compared to the late afternoon. That's an interesting finding. So that's shown by this. Sorry, this bar here in the top left. But then in rural areas, and also there's actually this pretty high correlation in the afternoon, approximately right at the TROPOMI overpass. So more work to be done here, but interesting to see kind of this displacement in time where there's highest correlation between the satellite and the surface monitors. I've discussed the prior HAQAST, so I just want to, I'll just talk about this very briefly. This is a paper published about 9 months ago now. Generally, I'm seeing pretty good agreement between the satellite and the emissions inventory from a magnitude standpoint when we look at, when we do this comparison from a magnitude, generally within 20%, more or less. But the main thing I want to highlight here is the satellite is having difficulty estimating NOx from some of these point sources. So typically the satellite is underestimating NO2 coming from the point sources directly, and we have some more work that's going to focus on this, but essentially it's some of the physics of observing very narrow plumes from power plants might be causing some of these biases near power plants only. One thing that we're working on also in Houston is this comparison between aircraft and satellite. So these are actually on the same color bar scales. And so very clearly you can see that the aircraft, the GCAS, making measurements somewhere around 20-ish thousand feet above the ground. I think it's maybe somewhere ballparking it. So it's getting all of the NO2 at the surface and comparing that to TROPOMI. And we see very actually excellent correlation from a spatial standpoint, but definitely an underestimate in TROPOMI. And that's partially due to the air mass factor, which we will correct for, and hopefully I'll have a new slide in a few months doing this comparison. But one reason I really want to show this is that really highlights the difference in point sources from TROPOMI versus GCAS, where GCAS can very clearly track this very high NO2 coming from this power plant and the Parish power plant west of Houston, whereas TROPOMI is able to capture it, but not the full magnitude of it. Finally, last slide here, I believe, is that I want to show some preliminary work by Dr. Geigert, who's showing how monitors versus models versus satellite are able to track NO2 disparities within cities. So here I'm just going to highlight New York City and show some of the other cities in a minute or two, where New York City, we have this. This is the relative disparities of NO2 by demographic. And we can see that non-Hispanic white generally breathe lower concentrations of NO2. Not, this generally shouldn't be surprising, but the magnitude is quite different. So statistical model and satellite saying it's 15% less, whereas the monitors are only saying it's about 5% less. And also, if you look at other demographics such as Asians and Blacks, it's just definitely a much bigger spread amongst those groups compared to what the monitors said. But so this is actually ends up being a pretty good case in New York City. If you look at, say, LA and Chicago, we're starting to see some much larger disagreements between what the monitors are saying the disparities are versus what the statistical models and the satellites showing. So the satellite and the statistical models are uniformly saying that the white population is underburdened in every city, but the monitors seem to miss this in almost every city. It showed kind of New York City was one city where it did get it, but not the full magnitude, but certainly LA, Chicago, it's not getting this, the disparities, I would say, correct. Yeah, I would, in this particular instance, I would say the statistical model and satellite are probably better predictors of NO2 disparities than the monitors, because they have just more spatial coverage. All right, so last wrap-up slide, I just wanted to emphasize, and I'll just go kind of the animation here, is that we have a group at Columbia and MIT working on trying to better understand uncertainties. They've done this for PM 2.5, and now we're going to do this for NO2. So more work to be done here that's using this BNE technique. I'm not going to go into the detail here. I'll let Arlene's team explain this at the next HAQAST, but really exciting that they're able to continue working on this project and better understanding uncertainties in NO2 data sets here in the United States. So with that, just some conclusions. I've discussed this. I think maybe I'll just keep this slide up and open it up for questions. I don't, I want to make sure there's about 5 minutes, but I can stay on later for those that are have additional questions. So thank you all for your contributions to this Geigert team. This is not just the science team pushing out data. I really encourage and really appreciate all the feedback that we've gotten from everybody throughout this Geigert team. HAQAST is not ending. We're still going to be around for the next 2 years funded on this project, but this particular Geigert team is ending and hopefully will emerge in some type of format and on a future Geigert team. So yeah, happy to take questions, additional questions.